Time check. Good afternoon. Good afternoon, everybody. Good afternoon to all.
Yeah.
I think now it is let us start the program. Okay, Professor.
Yes, yeah. Okay.
Sir? Yeah. Eleven, sir.
Yes, sir. Yes, I am
Okay.
hearing you. I am ready.
Okay. Let us start the program with a silent prayer. 1 minute silent prayer. Okay. Yes, sir. As a part of the World Statistics Day celebrations of Department of Statistics, University of Kerala, we are very lucky to have two eminent personalities. Our first two talks arranged, I think this is first talk is by Professor Arivarigran sir. Before starting the as a formality or otherwise, it is better all of you are aware that the Statistics Day celebrations are meant for certain objectives, to satisfy certain objectives. The one among them is to increase the public awareness of the power and impact of statistics in all aspects of the society. And second, the nurture creativity and development in the science of probability and statistics. So nurture statistics as a profession, especially among our youth or young people, and promote creativity and development in the science of probability and statistics. With this motive, we also join throughout the world. Everyone are celebrating World Statistics Day, in several platforms, in several ways. We also join with this on behalf of the Department of Statistics, University of Kerala, and the School of Physical and Mathematical Sciences of University of Kerala. We organize this program. As on behalf of them, I utilize this occasion to welcome each one of you to this international webinar. In this program, first talk is done by, we are all waiting for the first talk. Professor Arivargnan sir is a senior, retired senior professor of statistics and former HOD of Department of Statistics and Mathematics, Department of Statistics and Mathematics, Madurai Kamaraj University, Madurai. And is also the CSIR Emeritus Scientist Awardee, as well as UGC Emeritus Fellow Awardee. And he did his MSc from Annamalai University, PhD from IIT Madras, and DSc also from Madurai Kamaraj University. And he is the fellow of Academy of Sciences, Tamil Nadu Academy of Sciences, as well as fellow of Royal Statistical Society, UK. He has published a lot of works, and is a very eminent personality, an expert in the area of statistics, and in fact, associated mathematics also and computer science also is an eminent personality, expert. And I utilize this occasion to invite you, Professor, to give a talk on basics of structural equation modeling. I think this is the topic we have finalized. Even then, depending on the audience, he will do in a beautiful way whatever they like, they need. I hope, with the blessings of our great former professors, including our Kalyanaraman sir, Muthu sir, anyone is here, yeah, teacher, and former professors, with the blessing, with their blessings, let us start the program. I utilize this occasion to invite Professor G. Arivargnan sir to deliver the talk. And I hand over the mic to Professor.
Thanks, Professor. You said nice words on me. I don't know whether I am qualified to have all these words from you. I'm very happy to interact with statistics personalities, and I am seeing Krishnamurthy, Kalyanaraman, and other senior professors here. Thank you very much for inviting me to present here. Now my talk will be on structural equation modeling. From 1988 onwards, I think, because only during 1984 the software was released, LISRAD. That from the time onwards, I was somewhat associated with the STEM, that is structural equation modeling. But as a tradition, I was refined from using that. I will tell you why I was hesitant to use that. Because this is widely used in econometrics and psychometrics, sociology, management science, and little bit in genetics. And there are some reservations, not only for me, for many statisticians. Now I'll tell you why. Okay, now before that, I want to say something about the cause and effect. I think I should present my, but of course I will your entire screen. This one, share. Are you able to see this, Professor?
It's visible. Everything
Sorry,
okay, Professor?
You are seeing the presentation?
Yeah. You see, cause and effect relationship.
Yes. Okay. If anybody is not able to hear or see it, I just unmute your mic and say something. And if you find some mistakes in my presentation, and if you want to add some clarification, you are welcome. Now, actually, this cause and effect is an important area, but I would like to tell something about this. It's traditionally, or I should say, from the earlier human development, this causality, or some people say causation, cause and effect. We are all interested in trying to explain why certain things happen. Maybe we are evaluating a happening, look at the result of an experiment, by or wondering why this party or person won the election, assign a reason why your friend or somebody took a decision. For that, they need some cause. Actually, people were trying to answer this question, why this happens, or try to find a causal explanation. This behavior started very early. One more thing, I will not be spending on this for more than 10 minutes, but some explanation is very, very important. So causal explanation is a human-made concept. People thought only God, nature, people, animals, etc. could cause things to happen. Now, let me jump to particularly the storms, earthquake, and flood. They are thought to be controlled by gods. Of course, we do not assume that God is having any responsibility because we love God. But the erratic, unpredictable events such as rolling a die is not considered as a chance event. People thought that, I'm saying about this some past time, people thought it's a divine message. They demand proper interpretation. Okay. Now, I will go to the immediate, in general, I do not want to describe what happened in the attitude of scientists and engineers, and there is a small change because they're all speculative. They try to propose or try to convince people. Galileo, in 1638, he published a book. Of course, at that time he was in prison. His papers or manuscripts are smuggled out of his place, distributed at a faraway place. He gave two reasons, two principles, I should say. Don't try to explain. Describe first, explain later if possible. And second principle is describe in the language of math, namely equations. You may wonder why he's saying that. Just 50 years back from his time, the algebra was introduced in Europe. Algebra was developed by Arab people. It was introduced in Europe, and that was a revolutionary concept because people thought it's a language of mathematics. Now people start asking how to what if. Okay, I told you every science was a speculative one. Now empirical, that is, they observe, they conduct experiment, and try to connect events. Okay, now let us go to the next one. Particularly, the simple example of a flame leads to a heat. So people started assigning this as a cause, this is an effect. You may wonder why I am telling you all these things, because structural equation modeling depends upon the causation. But there is a very, very tricky and dangerous thing. If you do not understand what we mean, what is the distinction between causation or spurious causation, please note that. One fellow said, taking more alcohol lead to longer reaction response time. So it doesn't mean that if you want to have longer response time, you should take more alcohol. So the cause and effect, one causes some effect on other, should not be considered, but people were very fond of doing this. I can tell many more information about this, but that's not our area. Now, there is one area where the causation was not considered. Actually, they tried to explain causation and important differences between correlation. That is statistics. To say only two references, Francis Galton, a cousin of Charles Darwin, came up with the concept of correlation. In 1858, he measured the lengths of forearm and size of the head. His question is, can one be used to predict the other? Please note that at the time, people are trying to answer how this happens or why this happens, which causes this to happen. But he is not asking that question. Please read very carefully. Length of forearms, size of the head, are they related? He didn't use the word causation. So, can one be used to predict the other? So he coined the term correlation. So he said, correlation must be the consequence of variations of two organs being partly due to some common causes. Please think of this way: your head and your arm. If you have a longer head and a bigger size of head and longer arm, they are related. But in what way? There is some internal growth in cells. They dictate the size of the head, dictate the size of length of the forearm. So there is some common cause affecting two things. So people directly ask whether A affects B. He said A and B are affected by some other cause. That is the most important thing to understand structural equation modeling. Carl Pearson, a student of Francis Galton, was impressed. So, in 1911, he published the third edition. The book title is The Grammar of Science. Dear participants, please note that it's a book on statistics. He defined the new term, grammar of science. Well, if the new chapter, it is contingency and correlation. He used the correlation as a measure of covariation. Contingency is the discrete attribute data. There he coined the contingency and correlation. He said the title is insufficiency of causation. So what actually he refers to it, no need for causation, but he stressed on correlation. Please note that he categorically told correlation is a broader concept, causation is a limit or limited concept. He never used causation in his work. That's the most important thing that reflected heavily on subsequent statisticians. Exactly 25 years later, Fisher formulated the randomized experiments. You know what is randomized experiment? This is actually controlled experiments, a planned experiment. You have got some treatments to be compared on the yield. They have to conduct the experiment in a planned manner. So he gave three principles. One is a local control, randomization, replication. So these randomized experiments is the only science, only subject in statistics where the causal concept comes in. In no other statistical concept, we do not have a causal. So this is very clearly saying that don't have an observation study. I saw this, I saw that, this precedes that one, so this is the cause and effect. He said controlled data, controlled experiments that produced the result which is not confounded by or conflicted by some other variables. So I will come back later. Well, the quantification of correlation brought these people psychology, anthropology, medicine, sociology into a mathematical form. They want to study the concept of causation through correlation. But Carl Pearson told very categorically, correlation does not imply causation. He said it's a necessary condition for causation, but not a sufficient one. To fix our ideas, please think of a set theory. This set is actually as a collection of principles having a causation, here correlation. If you want to enter to causation, first enter to correlation, then you are eligible, then try to see whether there would be a causation. But if you are already here, there is a causation and there is a correlation. Okay. So this is an important point. The applied scientists, particularly sociologists and psychologists, are making some mistakes here. They collect data, they try to make a causation. Well, so I think this is my last slide I want to say. I think I have taken some 10 minutes. Okay. A correlation found in observation study may not positively indicate a causation. If you look at the everyday languages, they say some TV programs, they say this causes this, that follow one direction because of these things. Because they are making a speculative, their observation is very limited. But data from lab, what do I mean data from lab? If data is collected by experimental means, I told you experimental means local control, replication, randomization is taken care of. You think of some variables which will confound the results. In that case, you have to avoid that, right? Then only, or simply say data from lab, okay? Then only the causation does lead to causation, right? I think I made one important point for the basis of structural equation modeling. But what happens in sociology and econometrics, people just collect data, they want to propose a model, and they say this is my model is good or bad or like that. My model is significant, not significant. They make things, they make a statement like this. Now, I stop here. I move to the major presentation, structural equation modeling. And I was told that there will be a variety of people from student to learned statisticians are here. So I moved to jump to a model. I think if they are all statistician, okay, you will understand it. But I expect some students, some scholars from other area. So I have to say something about the model. Then I will go to from that model, I will build the various steps for a structural equation model. We are always interested in prediction of a phenomenon or a future event. Now, this example comes from my friend. He is in Madurai Commerce University. He was studying the behavior of bats, chronobiology department that is specialized in studying the bat. So, from his collection, I took some 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 values as a sample. These refer to the wing lengths of bat. They have to hold it from shoulder to the tip of the finger, longest finger they are measured. 1.4, I don't want to say it's a meter or feet, some unit. Now this varies from 1.4 to 5 or 5.2. So the data has a variation. Now, my question is, suppose somebody catches a new bird, I didn't see it, but what could be the wing length? So I use this data to make a prediction. So I make a total of these and divide by the 13. I get a mean value 3.45. So we always use mean to represent a class average, class standard, or the economy of a country, or so on. So 3.415 will be the length of an arbitrary band. I mean, wing length of arbitrary band. But we notice there is a large variation. So it's not a better estimate. So we want to improve our model. If we want a model that improve our estimate. So assume that I was also given the ages of the bat. So I got the wing length and we say age. Then I put it in the model. You can use SPSS or R software. You get the equation. Wing length equal to 0.713, 0.270 times age. This means for every 1 unit age, the increase in wing length will be 0.270. Now, if a new bird has the age 13, then the wing length will be 4.169. This is actually a better estimate. But one caution is, are they rated? So we may assume there are ways of verifying that the age and wing length are correlated. So we can say wing length relative to age. So this is the first model. I told you how to check this scatter plot, and the points are along a straight line. So this straight line is my model. This is my model. But all the points are not on line, so this is a deviation. So that is represented by a symbol E. So whenever we are trying to predict a phenomenon by some cause, some variables, then you would attach a deviation. I will explain why we are having this, but visually you can see that there is some discrepancies. Now, before I proceed, I want to pinpoint one important result. Here, the fit is not good because the line is here, the points are away from this. Okay. The line is not, the model is not a good fit. So, this particular aspect is heavily used in structural modeling. And I think you can see this if you are, yeah. So the data points are here. So the y-values are here. We can see that it varies from here to here. Of course, we have got a lot of measures of finding variation. We can use one of them. But once I have a fitted line, this is the estimate. This is the estimate for this particular observation. This is an estimate. So I consider these are the estimates according to the model. I put y cap. The variation is this. But if the points are not deviating from straight line, this variation almost equal. Rather, if it's not a good fit, then in that case, the points are away from straight line, then variations in y is so much or larger than the variation in y cap. So for a simple model, this gives an idea. You may ask, this R square. Of course, this idea we are going to use in structural equations. So comparing the variation of y, comparing the variation y cap, usually this root mean square deviations, we can use it. Now, if you are very particular about that is R square, I can derive here. Now I think it is almost 25 minutes passed. So I will move on to our step. So I am going to consider the building blocks of structural equation modeling. And at this point, I am not giving any advanced results here. I am thinking that some students are there, they do not know anything about structural equation modeling. They would like to know what it is. Once they understand, they can try to go to library and learn many more books or tutorials from web. They can proceed further if you are interested. So I am going to give only the building blocks. What is sum? You can think of a network analogy. Think of a network of variables. Connections represent some cause and effect processes, like a flow chart. process flows in one direction. This is important aspect in structure equation. No loops going to one place, coming back. I think I got somewhere. Yes, there is one example I have given. So this one structural equation, structural model, and from H you can go to F. H in affects G. F also affects G. Okay. Here, one factor, I'll tell you why what I mean factor and everything. These are the present, there are something circle boxes. I will explain. So there are various network I have written are drawn here. I can club this into this because F is here. F is here, H is here, G is here. I can bring this here. So you can think of a cluster of networks there. Okay. Now I will tell you what I mean. So the first impression is structural equation model is a collection of networks or a web of network. Okay. Coming about a linear regression, we assume cause has my effect on that. Now at this stage, please remember, somehow we have checked everything. There is no, there is a causation. That is simple. That is, we have taken data from a lab. That is after controlling every aspect of an experiment, planned experiment, having taken control of local control and implemented replication and so on. We are having a correlation. So that forces us to have a causation. So once you are assuming that there is a causation, that is a very difficult job in the applied science. But many applied scientists take this very, very simple thing. But that's why we statisticians are not encouraging this type of study. But if the X and Y are collected through a controlled and planned experiments, and there is a correlation, and we assume that there is a common base there, so X leads to Y, X causes Y. So we write this symbol. This symbol is a arrow. It's some sort of a graph theoretic concept. It's unidirectional. It can't come back. It will come back at some other place. I will tell you. Here X causes some effect on Y. To fix your ideas, think of how much time or hour you take for study and look at the exam marks. If you spend more time on study, more hours, then you can expect more marks. So this is a very simple cause and effect. But study hours cannot produce the same value or effect in exam marks at repeated observations. So we may need, that's why confounding variables, additional variables to explain it completely, but we are trying to remove this because I told you local control. Right. Now, since this X cannot explain the variation from Y, something is left over, I assign a error term. If you want to have an idea, then in the previous diagram, yes, points scatter plots, and there are some straight lines, and the border is the straight line, and the points are away from straight line. I think I don't want to go back again. Now, why I am adding error term here? Apart from X, Y may be affected by some more variables, which they are not included in the model or forgotten or it is maybe unknown. So in that case, to account for the variation left over by X, we use epsilon. So the trick is very clear. Look at the total variation here. Total variance by X. Are they equal? No. There is something left over. There is a variation in epsilon or error. So you compare this and this. If variance X is more than variation error term, we can ignore this. Unless then we have to redo the experiment. So that's called a validation of a model. Okay. Now some terminologies, and we all use the word independent variable, dependent variable, but in SEM modeling, we don't use the DV and IV. We use the word endogenous and exogenous. These two things are from Latin. Exogenous mean inside, endogenous is coming from outside, exogenous coming from outside, endogenous inside. So once you draw the diagrams, you will understand what is exogenous and endogenous. An exogenous variable causes endogenous variable. Okay. Now, whenever you have a causation, the affected variable will have one error term. There is one error term must be added to a variable. So if you want that definition, here, this is the exogenous, this is endogenous. Whenever exogenous affects endogenous, and we can use this to predict why there is something left over. So we always write this. This is very fundamental in structural equation modeling. So multiple regression. So I can go very quick. This multiple regression equation in structural equation modeling we represent x1, x2, x3, two variables affecting the endogenous variable. When we are using x1, x2, x3 affecting y, our intention to predict y, we can't do this completely. There must be error. That will be accounted by this term. That's why we have error term attached. So you can take it as a very simple rule. Whenever a arrow pointing to a variable, there will be an error term going towards that variable. Now, multivariate regression. That is you can think of this as a multivariate statistics. That is, this is a vector. Here is a model. You can write everything in terms of matrices you can deal with. But in some formulation, that exogenous variable affect endogenous. X1 may affect Y1 and Y2. X2 may be affecting Y1, Y2, and so on. As I told you, when Y1 is being predicted, error term must be added. This was included here. So far, regression. But what is a path model? In multiple regression, these are assumed to be independent. Please note that in our story. When I say this affects this, x1, x2, x3, x4 are assumed to be independent. Because we are going to use the least square principle. Least square principle requires this. All right? Therefore, in multiple regression, they are assumed to be independent. But people say in other sciences, particularly sociology, psychology, everything is related to another, one affects another. So assume that we want to have a correlation structure among exogenous variable. And in addition, we may want to have a causation from one y1 to this one. This is an independent variable, or in same terminology, it's a endogenous. This may affect another one. Well, in that case, I am going to have relaxation. The x1, x2, x3 are no longer independent. They are related. The endogenous variable has some causation. So, for instance, y1 affects y2. You can't have both. y1 affecting y2, y2 affecting y1. That is called a loop. It is not allowed in path modeling. Okay. So, I have redrawn. x1 affects y1, x1 affects y2. Then these are being affected. There is error term. Now, these exogenous variables are correlated. We are using this type of symbol to represent correlation. A one direction arrow is a causation. This universal terminology, this is needed to write equation path equation in software. Please remember that this structural equation modeling cannot be solved by hand. You need a software. But you have to convey your path. Some software allows you to draw the path. Some software allows you to write equation. Okay, therefore, this is a correlation. This is a causation. Now I am building a one model where this is I am hypothesizing this x1, x2, x4 affects this, and they may have a correlation, right? So important difference between multiple regression and path model is exhaust variables they are correlated. If you assume independence, this is nothing but your useful multiple regression. Now, I am going to say a word observable. That means I can measure it. If I find some concept, some phenomena among some people, I may count it, get the value, numerical value, or I may measure. So in general, I am going to use the word measurable. A measurable variable is called observable. But sometimes some variables are unobservable. That's why sociologists and psychologists and management people wants to study the consumer expectation, consumer satisfaction, and so on. They can't be measured directly. They use some other technique. So here I am going to call this hidden. Another word is latent. Okay. So convention, observable variables will be put inside a box and latent variables will be put under a circle. This was started in 1984 when the first SEM model was introduced by Zoraksberg. He wrote a software. So in his notes, he started doing this. Now, faithfully, everybody is following it. It's an important convention. So in simple linear regression, X and Y are measured. This is age, this is wing length, but this unobserved. So I am putting a circle here. Here are boxes. This is a convention, universal convention. So how to the causing effect? Some people write from right to left, but I use the convention causing effect on left side, the affected one on right side. But what about this? This I need to draw this way, or I can put like this. I think I have shown here as right. So usually we time pass from left to right. Time axis, x-axis, y-axis from left to right. So it is convention. This is not a very stringent condition. Sometimes we may change depending upon the area available, because a complicated network will be drawn with many nodes, many nodal web or cluster of networks. Okay. Now, please remember that when I put a X and Y, some box and a circle, I meant this measurable, this not measurable. Now, when do we have unmeasurable things? Sun's flame, observable but not measurable. So you must have this distinction in real life, but in statistics, when you are not able to measure, you are not observing it. If you say I am observing it, you are able to measure. But for this example, sun's flame observable, but it causes change in the temperature, which can be measured using a barometer, some device. Similarly, intelligence is not directly measurable, but using marks you can measure it. And if you consider English, language, math, stat, physics, these are measurable. But numerical ability is not measurable. It's a phenomenon you can't observe, but you can use math and statistics, physics to using those marks, we can try to represent numerical ability. English and language, they reflect upon literary mastery. So this numerical ability and literary mastery or intelligence, they're all not measurable, but only through other observables. Okay. So I am going to rate a factor model. So these are English marks, language, maths, and so on are some collection of marks. We expect intelligence affects this and this and this. So a factor is put in a circle, unobservable, and these are measured. And when a arrow points to it, we are trying to predict the x1. Actually, we are not trying to. The factor actually trying to influence x1. The factor affects x2. Intelligence affects math mark. Intelligence affects English. Intelligence affects physics. But it can't be fully explained. Therefore, we want to have an error term. Okay, now move to the next one. See a difference. A multiple regression and factorialization. What is the difference? Look at the arrows. The arrow goes from a measurable quantity to a unobservable, a latent one. Sorry, I made a mistake. Yes, I will look at this first. I am talking about this one. These are all observable. You have got a causation. But here, in the factor model, the causation occurs from a latent variable. We are not able to see it. We can infer it, but we can't measure it. This affects x1. This affects x2. So you can see the direction of arrows to decide whether we have a causation from which variable on which. So a simple trick is if you have correlated exogenous variable, it is called a path model. If you are having hidden variables or latent variables, it's called a factor model. And the most important thing, I'm going to represent manifest variables and measure variables. When you are able to observe, measure, they can be simply called exogenous, but depending on the context or situation or application, they're either called indicators, manifest variables, some variables. I will come back to it. So the important thing is a combination of path model and factor model. A combination of a path model and factor model is known as a structural equation model. So far I have been talking in general. Let us, how much time I have? Okay, I will rush to anxiety. This is a study on anxiety among women. When the kids they have kids, they are in general anxious. If they are isolated, they still have anxiety. So you can propose many models. There is kids brings isolation that leads to anxiety. This one point. Or isolation creates anxiety. Kids create anxiety. This is another model. Kids may bring anxiety. Kids may bring isolation because when you are having kids, you can't go out. You are isolated from your friends. So your anxiety may be due to kids, or due to isolation, or the kids may have indirect causation on anxiety. Now, isolation is called a mediator. Here also, kids is not having direct effect. It's a mediation. Well, now I think we are right. So, important point is that there are many models. For instance, we have got 1, 2, 3, 4, 5 models I described. You may ask one question: which model is the best one? This is a general question asked by a psychologist, a sociologist. When they contact me, I told the question is wrong. The correct way to ask is which model best fits the data on hand? Which model could have produced your data? So the important thing, which other scientists fail to understand is the sum will not find you the good model. If you specify a model, it will say whether it's a good or it will evaluate whether it is good or bad, right? I think I can just jump to, for instance, I have a model here, 3 exogenous variables, they are correlated, they affect y. This is one hypothesis I am having. I can draw in many ways, many different models are available to you, and assume that I propose this model. The x1, x2, x3 are and y are observable. Assume that it is a result of a controlled experiments. You can get the correlation matrix. This one is correlation between x1 and x2. This x1 and x3. This x1 and y. Similarly, x2 and this is x3. X3, x1, x2, x3. Here, this is x3 and y. This is x2 and y. Okay. Now, this can be obtained because x1, x2, x3 and y are observable or measurable. We can find the correlation matrix and we propose a model that is this effect, they are the correlation. Now, the interesting thing is how to find our, this is called path coefficient, this path coefficient. Actually, at this stage, at this time, we can think of a simple idea. There, in one way, it's a slope of a regression line, or it's a partial correlation. So these represent the actual effect of y x1 on y, right? Now, how to compute this? This is an important. This result I have taken from a genetist, and actually, it is proposed by a genetist, right, in 1934. Please note that structural equation modeling started in 1930s onwards. Actually, when Spearman started about the rank correlation, in itself, the factor model arose, and subsequently the structural equation modeling. Now, I would like to say something using this matrix. I want to read this. This is the A, B, C. I want to find out D and E, F for correlation, which we already computed. Now, what is the effect of x1 on y? Naturally, A, or you can go to x2, then come here. So D into P is another effect, then E into C another effect. So we call these two, DB into EC, as an indirect effect. A is a direct effect. So total effect is this. The computation of the total effect in terms of direct and indirect is helping applied scientists to interpret certain results. Okay, I'm going to say a result. There is a hand computation. R1Y. The correlation from x1 and y is composed of A, D into B, E into C. DB into CE. Similarly, you can write the equations, and I give the values, the 3 unknowns, 3 equations, you can solve and get it. Okay. So this is the way I was doing in 1980s and 90s, because those days we did not even have a calculator. The calculator came around 80s, I think, late 80s, sorry, late 70s. So we have to use a paper and pencil to do the calculations. So at this time, the path coefficients are nothing but standardized partial regression coefficient. The partial regression coefficient, don't worry about the standardized, because when you consider each variable, subtract the mean, divide by standardization, you got a standardized. Now, partial regression means if there are additional variables, only one variable means regression. If there are many variables, You have to avoid the influence of those variables. That's why we say it's a partial. Professor Statistical, how
Yeah,
much
yeah,
time?
yeah, Professor.
At,
Uh,
at what time I have to stop?
you can take 5 more minutes, Professor.
Okay. Okay. Now, in that case, I will describe certain examples. With that, I can stop. Now, I'm going to consider some examples. A simple regression model is this. The food preference is actually influenced by food taste, quality, or nutrition. So, at restaurant, people would like to know which actually influence the food preference. So, if they know about it, then they can make concentration on that particular variable. So, you take it as a simple multiple regression, collect data, then find the path coefficients. A, B, C. Depending upon the A, B, C, you can make a decision or you can test for the coefficients. Well, now the purchase, desire to purchase some jewels or something is here. It is affected by the income. If a person is having more income, he wants to purchase. If a person wants the desire, anxiety, he'll purchase. If you do that assuming any coordinate structure, it's a multiplication. If I assume a correlation between income and anxiety, because that's always there. Status people conveniently assume they are independent. The independent variables are independent. That's what I think. But psychologists and so management people say if there are more income, anxiety is there. When the anxiety is there, they will try to get more income. So this is a picture of multiplication. This is the path model. And now, again, I told you about the language and English, math, stat. People try to find what is the underlying hidden variables. Somebody may like to propose only 2. You can think, why not 5? That's not a good model, minimal. So, subject to the structure and computation, you may get some arcs will be removed because they are very insignificant. In the case, finally, we know which variable affects which latent variable affects which variable. So that's one important point. Another factor model, I think this also I can rush through. I think with this I can close it. A study on customer satisfaction. A manager proposes the perceived quality and customer expectation are the 2 variables, they influence the CS. So he proposes, we draw this perceived quality and customer expectation. When you want to buy some toothpaste, we get some tonight as this particular point is good, but it's not good. So we have got some perceived quality and our expectation. Both things will lead to customer satisfaction. But both these 3 variables are latent variables. That's why I put a circle here. So I am going to design a questionnaire. Suppose items, let us call it PQ1, PQ2, PQ3 set of questions. They may ask whether you like or you dislike. So 7 point or 5 point, like Likert scale. Use a Likert scale from 1 to 5 or 1 to 7. Using that, you ask what is their perceived quality. Similarly, customer expectation, you can ask them questions or items. They seek response in a Likert scale 5 or 7. Here I have to draw very easily. I have given 3 and 4, here 2. Please note that this is error. Why? When arrow comes here, it's error. When arrow goes here, there's an error term. Okay. The arrow comes here, this error term. In real project, you may have at least 10 to 20 items for this and another 15 items for this. In one of my consultancy project with quite there is a information security awareness There I got 7 variables, nearly 100 odd items. So I have to propose. I have to spend more time on with the people who conducted the experiment. Then we try to group them into which will represent my latent variable. I prepared some latent variable with them. So latent variable, how they are related, and which is affected by this perceived this latent variable. So this actually gives a freedom to people. If you ask a statistician, he will say this and that. But people always go for immediately a study. So what they think if a study is longer, larger, and more variables, they can always come up with a good model. They can analyze because now computer softwares are coming in. Now the final slide I think I can this is Professor. I can have 1 more minute.
No, sir, sure, sure.
What are the approaches to solve ACM? Covariance-based method. This more or less similar to what I started in the beginning. The Y values variation. According to model, you get the Y cap or Y estimate. That has variation you have to compare. That is called covariance-based. Okay. But the problem is this is the first model. This is the oldest method proposed, and this was invented by Jorisberg. He wrote a software. I saw this software in a mainframe computer in IIT during 1983. That is the only software available. So around nearly South India, people went to IIT Madras to process the data. Now, with the advent of computers, you have got many more software coming, but still Ristel is a leader. And the new thing is just 10 years back, people came up with the idea of partial least square. And if you look at the partial, you may be thinking that it's very complicated. We know what is least square. In linear regression, we use the least square. But partial means you have to avoid certain cluster of web, use the least square. That's the idea. And there are many more methods. I use a principal component regression. And with this, the approaches can be 2 things. One is covariance based, another PLS SEM, one is CB SEM. And you cannot have a hand computation. You have to plan, prepare, and prepare the data, take a sample. You have to go to the computer. There are many more softwares available. Professor, I think I can stop now because many more things are here. I don't want to say all those things. Okay, some simple description I have given. There is my. I'll come back to the audience. Professor, you can
Thank you, Professor. Thank you so much for the excellent talk.
Thank you. Because you told that there will be a wide range of variety of people there, from students to scholars. So I tried to only basic things. But without understanding, you can't go to this. Yes, sir. Please.
Yeah, Professor. In fact, several are waiting for. In fact, we can also do something in future also. Continue some related work.
Okay.
I 1 or 2 can ask any your doubts. I think or anything if you have. Otherwise, you can contact Professor through email, and you can also put your doubts in the Facebook page of in which we have live stream start to done through Facebook page, and also to YouTube also we will.
Yeah, I hope this is available on YouTube.
Yeah, and we will record it. I think.
Okay. I think I can see the diagram. Yeah, there's a
that. So, if anyone is really interested to ask question, please 1 or 2 is nice enough. Please. And
Sir, what is the difference between SEM and AMOS? Are they the same?
There is AMOS, then Israel.
Yes, sir. AMOS.
AMO is a software that implements the, I told you, the component-based, covariance-based structural equation modeling analysis being carried out by Lisser as well as SEM, EMOS. Lisser is the original inventor of the computation method, Johannesburg. EMOS is a separate company. The company, the SPS purchased that product, they made it available with the SPSS. Without SPSS, you can also use the AMS. Both are one the same. They're different company products. That's all. Different company products.
Sir, is is AMOS extension of SEM?
No, SEM is a general methodology, modeling process, computation process, structural equation modeling, incorporates modeling and analysis. How it is implemented? This is the covariance based method. The methodology is there. And unfortunately, there are some equations that cannot be, they're not linear. I mean, they are non-linear. So there could be a difficulty in solving that. So people try to use various algorithms, iterative algorithms, right? So both use the same algorithms. They get the same result. I tried literal and AMS, I get the same answer. Okay. Literal is a different way of executing that SEM, whereas AMS is in different way. The methodology is different. That's all. But they both implement the same algorithm, they get the same result. Not only that, EQS, there's a new other software that's also implement the same algorithm. The algorithms are not different. See, when you have the different algorithm, where do you start the algorithm or iterative process? At what point you start? That is going to matter. But finally, because they are iterative again and again with the computer, a large number, finally they arrive at the same result. AMOS and literal, EPS, and what else? MX. They put the same algorithm of covariance based. So the result is not different, the same thing. The only thing is
Sir,
PMS is different. Yes, sir.
sir, can I have, sir?
Yes,
Sadish,
yes,
sir?
yes,
Yeah,
sir.
you
Sir,
can
Yes.
continue, please.
sir, I'm Dr. Harjendra Kumar from Pondicherry. Thank you, sir. Thank you for
Okay,
hosting
okay,
this one. It's a
okay.
fantastic topic. And it's a
Thank you.
topic of my interest as well, because my
Yes, sir.
area of interest also. So thank you
Okay.
very much for the presentation, sir. But I
Thank
have
you.
some few queries on it. First thing, because one slide you mentioned that, so for example, if it's a control trial, for example, if it's a control trial, let us suppose, yes, we are doing an RCT. Even if in the control trial also, can we say that correlation leads to a correlation and causation
Okay.
uh, can be same? Is it same? I would say that because see, whenever if you are using an RCT also, there are a lot of collinearity. So collinearity
Yeah.
will exist even if it's a controlled trial as well. So
Yes.
if there is a collinearity, definitely correlation will not lead to causation. So that is my understanding
No, no, no.
on
If
it.
I said actually, that's what we call spurious correlations. Okay, when the number of doctors in a region, number of patients, you can see this they are correlated. But it doesn't mean that there is a causation. So correlation
That no,
is
that's what I under,
yeah. The
that is what
correlation
I
need not
understand,
be
sir.
played. No,
Correlation
I
is
want
for
to
association.
yes,
Causation, all association will not lead to causation, but causation
yes,
there will be an association.
yeah.
So
That's right.
even in the
That's right.
control trial also we observed that many times. Many times we
Yeah, yeah.
observed that in
Causation
the
always
control trial
causation.
also,
So
yeah,
as
causation is always correlation.
I want to add this. Carl stated as it. The correlation is a broad concept. Causation is a narrow concept.
The
Yes, I can hear. I can hear. I think there is a disconnect with them. And there one more thing, sir, I want to tell this thing, because this technique is a very powerful, and as SEM, structural equations modeling, it is one of these good abilities to account for the measurement error. Okay, one is a good advantage of this one is account for measurement error. That is lacking all our conventional statistical methods. All conventional traditional statistical methods will not account for measurement error, but structural equations model we can have. That is one thing. Second one, how to accommodate the multicollinearity. So multicollinearity is
that is one of the we always get in multiple regression. Okay, that those difficulties which you experience in multiple regression also comes here. You take care. Yes.
Yeah.
But that's why people
that is what
towards PLS. PLS takes care of everything. See, I want to add this. 1 minute, sir. Actually, the covariance-based has got a lot of restrictions. Non-normal data is very difficult to analyze and has very collinearity. If more variables means the R square will be affected. Therefore, better you go for the PLS, partial least square. This is actually, there is a important paper. When you should use the covariance-based, when you should use the PLS, partial least square. There is a distinction. If you are very particular about the multi-coordinate, you go for PLS. Yes, madam.
Sir, even if we are going with the CB based or what is the PLS based, yes, we just make a comparison between these two models, SEM based on CB and PLS. Yes, I tried it. Yes, with my data, and this is my research. So we find it much different between these two.
Yeah,
more importantly, as far as the applied level is concerned, CB based, because when you are with the multivariate, we are always dealing with the variance covariance matrix, and we were compare the variance covariance matrix of observed with the what is called estimated. That will be the more robust way of doing SEM as far as the applied science is concerned. So that is what we found.
Mr. Dr. Harchit, please raise your camera. I am seeing only your table.
Yeah. Okay, sorry. Okay, here we see.
No.
So
when I see your face and your voice, I get more clear.
I'm sorry, sir. Yeah. See, now is it okay, sir? So
okay.
We met many times, sir. That is why I'm interested in it, sir. Yeah. So, sir, I did it so I'm working in medical research in Jipmar Pondicherry. We have been using this method for quite a long time, structural equations modeling and all.
Which software you are using?
Amos. Listener, Amos, Stata. And we are just...
I started with the Listener. You have purchased the software, I think.
Yes, we have. And we have a SAS module also for it. And sir, because my PhD is also the same line. My teacher is there. Sorry, I did my PhD and Sadish sir is the teacher also. Yeah, sir, it is a very good talk, sir. What I feel that this is one of the area where we can concentrate, but people are little neglected towards this one because of this complexity. Because we are just developing a conceptual model and we are testing the data for this conceptual model. So if it is not ready, because we are fine-tuned this conceptual model, keep on fine-tuning till we get. Because of this complexity, many people are hesitant to use it. And this technique is widely been used by these commerce people. I mean, the persons who are doing research in commerce. And it has a lot of potential. The person who is interested in biomedical research, it has a lot of potential because of the complexity. So people are not using it, and that is why I thought it's the right time. Sadish sir has taken up this one, and right time you just given this talk to this the students, sir. Thanks to you, sir, and congratulations to Sadish sir and his department, because we know that the most vibrant and dynamic department. They are hosting a lot of things, and thanks to you, sir, Sadish sir, for organizing this fantastic work. Thanks to you, Ariviran sir, for a fantastic talk also.
Thank you.
Thank you. Thank you, Professor. Thank you so much.
Thank you.
Other doubts you can later. We have, in fact, once again, on behalf of the Department of Statistics and the School of Physical and Mathematical Sciences, I extend and all assembled through this link, Google Meet around, I think now 58 or around 60, and other Facebook also watching several, then probably 500 something, I like so. On behalf of all of them, I extend our heartfelt gratitude to Professor Arvind sir for
Thank you very much.
your
Thanks for allowing me to talk to your people. Actually, I am one of the beneficiary because I studied a lot of references on books for preparing this. I am the one who is very much benefited. Thank you, Professor. Thank you.
Thank you so much. Yeah, thank you
Thank you.
so much. Now our next speaker is of this day, this great day of World Statistics Day, is our Professor Violeta E. Piperigo. She is from Greece. In fact, she is from is a professor from Division of Statistics, Probability and Operation Research, University of Patras, Greece. She did her PhD at the University of Athens, and she did a lot of works in the area. And I know her from, I think, 2003 onwards through her paper, and a joint paper with Papaguru, I think so. And while last year I was there in the Grand Rapids, USA, in connection with a conference in Michigan Central University of their Professor Violeta is waiting for me, and we met there, and she is a very excellent in the area of distribution theory, especially in statistical modeling, discrete probability distributions, multivariate probability, copulas, and applications in actuarial mathematics, etc., etc. And I'm very much glad to have a person like her to associate with our department in connection with the World Statistics Day celebrations. In fact, she did a book also on the parametric statistical inference, and she did a lot of works, and her works also cited extensively in the literature. With great pleasure, and on behalf of the Department of Statistics, University of Kerala, and School of Physical and Mathematical Sciences, University of Kerala, shall I invite you, Madam, to give something from your area, and several are waiting for your talk. Thank you so much. With once again inviting you, I hand over the mic to Professor Violeta Piperigo.
Thank you very much, Professor Kumar, for the invitation. I don't know if you can hear me well. It's a pleasure to be there and an honor to be there with you. And since I'm coming from far away, I decided first to spend some time to present my university and this one of my origin. So Violeta is my first name. The first name here goes for Greek people, and that's the middle name is my father's name. It was Stathios, and I come from the University of Patras. It is the Department of Mathematics that has a division of statistics and probability. And here we are to celebrate at your institution the World Statistics Day. And so let's first begin with a few things about the University of Patras. Actually, a lot of images and the city of Patras and its history, and how recently all these have affected my perspective about real data and statistics. So let me show a little bit about my university. That's the main building of the university, and this is our crest, and it's St. Andrews, the disabled who was killed here in Patras, and so his body is somewhere in our church. And let's see.
Madam, you can present to present now button in the bottom. Can present.
Oh, I'm sorry. I'm sorry. I'm sorry. I haven't. Why so? I have. Let's do it again.
Yeah.
Okay. Can you see it now? No, you can't.
Madam, no, you can't.
No, for some reason.
Yeah. Now it is coming.
Okay. Yes, I'm so sorry. You see, we are using Skype for business in Greece, and I'm not familiar. I'm so sorry. Let me make sure that you see everything now.
Now it is
Okay.
Yeah.
The first comment was about my name, because I'm always confused with your name. So I have first to say that's my first name and that's my family name, and this E stands for my father name. And so I come from the University of Patras. There's a department of mathematics. There's no department of statistics there, but there is a division of statistics and probability within the department of mathematics. And I shall first say a few words about the university, the city of Patras, its history. And since we are celebrating this World Statistics Day, I'm going to talk a little bit about the Hellenic Statistical Authority and the data that can be provided by this authority on regional and national level, and how these data have affected me recently on my research. So that's the main building of our university, and you can see details on our study programs and so on. But let me first show you a little bit the map of Greece. Greece is a small country. We are only 11 million people, and there are 4 million people in Athens, almost 1 million in Thessaloniki, and here in Patras, we are just 250,000. So it is not, it's the third largest city in Greece. Of course, you are all familiar with the islands and the big island of Creta here, and the Ionian Islands, Aegean Sea. Turkey is on our east, and Albania, Fyrom, Bulgaria are on the north side, and somewhere here is Italy. So Patra used to be a very famous port to the West Europe and to Italy. I shall talk to you about it. Okay, you are watching everything. So the University of Patras, it is the largest, the third largest university in Greece, and it has academic staff and laboratory staff and administrative staff, and almost 30,000 students. This is a big number for Greece. That's part of our campus. Somewhere here is my department, Department of Mathematics. We are together with the biology, and here is the main building you have already seen earlier. So some photos from our campus, the library, there's a big conference center inside the campus, and also there's a hospital. That's a famous bridge that joins the West Greece and is the longest wired bridge in Europe. And here is my department. Is one of the oldest department of the university, and we're few these days. We're actually less than 30 staff members, but we have enough students and postgraduate students and PhD candidates. So here are our students, and these are some of our faculty members. It was a gathering, a congress that we had last year on big data. It was organized by our division, and some of the students are already PhD students abroad, because it's a photo taken 2 years ago. And of course, there are postgraduate studies in our university. There are many new postgraduate programs, and of course, we encourage Erasmus and Modus exchange, and there's collaboration with various countries on that type of programs. The ranking is something that is important for our rector and vice rector of academic affairs, so they try their best to be ranked our university by various organizations, and we're doing good. I'm not giving the numbers here, but I would like to insist a little bit on the Erasmus. There are many agreements around Europe, and there are no agreement with India yet. So if you're interested, we might discuss this later. There's an Erasmus agreement with universities in China, but not yet in India. So that's some aspects of our city. As I told you, it was a port, and let me show you a little bit of the ancient Roman theater that is in the middle of the city, and the modern theater that is a replica actual of the Milano theater, the Scala, and it's the oldest theater in modern Greece. And when we say modern Greece, it's after 1831, when we were liberated by the Turks. And here is the museum, the archaeological museum. There are a lot of frescoes and mosaic from the Roman time of the city. But I would like to speak a little bit about the commercial period of Patras, and it was a port of exportation of agricultural products, mostly raisins, and you can see here the process with the grapes, and then they were packed in barrels and they were sent away. So it was urbanized, and there was a lot of wealth, new buildings, and people. But at the beginning of the 20th century, there was a crisis of all this commercial resin business, and so it has the city to change its perspective. So it becomes the industrial period of the city, and there were industries that were inaugurated, like paper mills. You can see one of these paper mills, and cotton manufacturing. Actually, this was the biggest company in the whole Greece, with many factories all over the country. This business, they were progressing well, and they were also new business on chemicals and spirits. You can see these old photos, and here these big, huge barrels of wine, a special wine produced here. And these are something like 150-year-old, these barrels. They are taller than me. And it's the famous Achaia Claus winery, but also wooden timber, and later on, car tires by Pirelli. But all these companies, they were shut down by 1990. 1991, actually, it was the last time that Pirelli worked. The winery is still here, but it's actually a museum, not a productive industry. So that's a difficult period for Patras, and in fact, the only industry right now is the university. And this restructuring of jobs had, of course, a lot of influence on local people. But since we are here on a Statistics Day, And the theme of this day is connecting world with data we can trust. I would like to say a few words about the Hellenic Statistical Authority, where one can find a lot of numbers about our economy, the various indices, population, agricultural, industry, trade, services, all these economic branches that make up the domestic product. And of course, it's easy now because everything is digitalized and you can have all these numbers in the form of an Excel file. And so you can have all this data. And I was approached by some colleague from the Polytechnic School who were interested actually in this restructuring of Patras from the agricultural time to the industrial era and then to the present, where services and other branches of economy are present. So you can see the green is the people on the left axis that are engaged in agriculture, and we are in 1980. It's the beginning of this crisis that ended in 1990, where all this industry closed. So you can see how agriculture diminishes. That's the entrance of Greece in the European community. And then there's a construction sector. And here is the trade and the tourism sector. And you can see how personnel from one sector goes to another sector and how this affects our income. So that's an ongoing discussion about this thing. We're going to use regression theory to analyze this data. And of course, they are discrete data, as I'm interested in the personnel that are engaged in each one of these economic sectors and how this number of personnel affect the gross domestic product, which you can see it here with the peak a little bit after the Olympic Games of 2004 and the decline that followed the last years till now. So that was the first part I would like to show you. I don't know if you would like to ask something before proceed. So the second part, I would like a little bit to explain where I come from. And when I say where I come from, where my family comes from, where I had my studies, and which were the people that influenced my research interest, which are in distribution theory. And then I'm going to talk to you a little bit technical about generalized distributions that can be used for analyzing biological and accident data, and how copula models can help also in revisiting this data differently. So I come from Delphi. Delphi is called the navel of the world, and there you can find the shrine of Apollo, the temple of Apollo. The remains of the temple are here. And you can see also the theater. In the shrine of Apollo, there were the Delphi oracle, Pythia, which was giving the prophecies. It was a lady, an old lady, and they were the priests that received the questions from all the people that were addressed to the shrine to find about the future. And there is a myth that Delphi is the navel of the world because the god sent two birds, one to the east, one to the west, and the two birds met here. So here is the navel, and that stone navel represents the fact. You can see here reconstructed the whole archaeological site, and you see there are small buildings that are called treasures apart from the main temple. In these treasures, various cities, not only from Greece, but what we say the Great Greece, all the colonies, that means cities around Mediterranean Sea, even from Marseille in France, from South Italy, from Minor Asia, they were bringing here offers to the god. Here is the treasure of Athenians, the city of Athens, and some of these statues are offers. This is the famous statue of Aeneas, the chariot. It's a bronze statue, and look at beautiful eyes here. And there's a big bull, a silver one, and here is the remains of a statue of Apollo. It's ivory and it's gold. So that's where I'm coming from. And you can see the modern village. It has been sifted in order to have all this excavation. Here is my mother house of my mother, her family, and you can have this view that's a valley full of olive trees. A little bit further, there is the European Cultural Center. It's a place for cultural events, exhibition, and there I have heard for the first time famous mathematicians that visiting Greece for scientific conference, and of course politicians for political congresses. And one of these was Indira Gandhi, who visited Delphi in 1983. Here is at the European Cultural Center, and here is in front of the Temple of Apollo with the Ministry of Culture, Melina Mercouri. She was an actor. And I did my studies at the University of Athens. It's a central building in Athens, and it's the oldest university in modern Greece, inaugurated in 1837. The Department of Mathematics is not in downtown Athens. There's a huge campus outside Athens, and so there are concentrated all of the schools they are. And there, at the Department of Mathematics, there was a leading personality, Professor Theokakoulos. He is not anymore with us. He passed away in April. Here is Professor Kakoulos. I was present at that Congress for celebrating his 65th birthday, and they were eminent visitors. It was Anderson, it was Chernov, it was Sober, it was Orkin, and of course, it was Sierra Rao. Here is also Sierra Rao, but it was not the first time that Rao visited University of Athens. In 1976, he had received an honorary doctorate from us. During the conference, it was another Indian professor with him, Naravayaswamy Balakrishna Bala. So that's a recent photo I took, and it was during a talk Bala gave at the Department of Mathematics. Calculus is here, and all other professors from that department when he was also given an honorary doctorate in 2016. So these people influenced me a lot, and calculus has worked a lot on distribution theory. Actually, my advisor, Professor Papageorgiou, Professor Kumar mentioned him earlier, has worked a lot with calculus, and so my research interest go to distribution theory and attended several conferences on this. One, it was on multivariate distributions with fixed marginal in Estonia. I'm going to give you some results from the paper that I presented there. And of course, the recent one, when I met in person Professor Kumar and Dharmaya and Nair, and I don't know if they are today in our audience, these beautiful ladies I met there. But I have visited India as well. And not only I admire the work of Indian scientists, but also I was really amazed by your way of living and your way of going ahead and how you progress. I have visited this January. It was the beginning of the COVID measures, actually, but I managed it well. Amity School of Engineering for a confluence that they had there. Some of the students that attended me, and of course we had a visit to Taj Mahal, not to a Hindu temple, unfortunately for me. So let's talk about discrete data. And I'm sorry. Is there a technical problem, Professor Kumar?
No, Professor. Nothing. What happens?
I don't know. Can you see the transparency? No.
Any technical problem?
Oh. Okay. Is it fine now?
You can see your screen.
It is visible. Your screen is visible, and your audio also visible.
Can you see the transparencies now?
Hello? Yes?
Can you see the transparency? Okay. Okay. So let me talk about discrete data and first describe a set of biological data that were given by Holgate and present some data about two species, the Protein guinans and the Lacystem aggregatum, that they have counted in a rainforest. And how do they do so? We count in each one of quadrats that are placed in the field how many of the two species of trees exist in each one of them. So it seems that there are a lot of quadrats that they have none tree of either types, and there are some that they have one tree of the Protein guindans, some other that have only one tree of the Lacystem aggregatum, and you see it's rather a short table of bivariate data because we don't have more than 4 or 5 observations, and we have an excess rather of the 0, 0 cell. That means not many aggregation of the two types of these trees. The usual distribution that is used for bivariate discrete data is the bivariate Poisson. However, when clustering is observed, then we have to make more complicated models in order to be able to estimate the data and the parameters of this model well. So when we have quadrats like these, we observe that there's some clustering either of the same type of data or of different types of data. And we are interested in the coverage, for instance, of seaweeds and seagrasses, or counting the invertebrates in each quadrant. So here we were talking about two types of trees. When individuals are dispersed in clusters, it might be plants, it might be the propagation of root systems, for the animals the competition, and for the shops also the competition of customers. These are reasons that justify the clustering of these populations. And how this clustering can be reflected to a mathematical model. In order to reflect clustering, when we are talking about the total number of individuals under study, let's say S, that is the total number of individuals, and XI, let's say X1 is the number of individuals in the first cluster, X2 is the number of individuals in the second cluster, Xn is the number of individuals in the N cluster, but N is not fixed because N, which is the number of cluster, is also a random variable itself that follows a distribution. And usually in discrete distribution modeling of this type, we are using the probability generating function of, let's say, the variable n. So u to the n multiplied by the probability for all different values of this discrete random variable. xy is the cluster size, okay, and it has by itself a discrete distribution because we are counting here trees. So the total distribution, which is called either randomly stopped or contagious or generalized, there are many names depending on the book that we are going to read about it. I'm preferring generalized distribution, can be written in a symbolic form like this, the distribution of the number of clusters generalized by the distribution of the cluster size. And so we can obtain the generative function of the total number of individuals as the composition of the generating function of the two generating functions corresponding to the number of clusters and to the number of individuals, the cluster size. So that's a basic model for generalized distribution in one dimension. And from one dimension, we want to go to 2 dimensions. So in the bivariate setup, we can have 2 different modes of densities for the joint number of 2 different individuals. So each one of these marginal distribution is like the previous one, but then we have to model dependence. So either we have the number of clusters that contain individuals N1 is the number of clusters that contain individuals of the type 1, and N2 is the number of clusters that contain individuals only of type 2. So these individuals are independent, but are dependent the number of clusters. So they are separated, the two type of individuals we are talking, but their clusters are not independent, they are dependent, and the dependence of these two random variables allows the dependence of the total number of individuals. So x1, x2, which are the number of two types of individuals, are independent. And now we have, using the same argument of conditional probability, the probability generating function of the number of individuals in both clusters as the common as the joint probability generating function of n1 and 2, and inside there is the marginal probability generating functions of x1 and x2 respectively. This is the first way of having a bivariate model, but it can be done also differently. The number of clusters is common, but in each cluster we might have two types of individuals. So they have a joint distribution, the type of individuals inside each one of this cluster, and this is, I might say, the simplest model, as I have a univariate distribution here as a probability generating function and the bivariate inside. So I have these two alternatives, and these produce a lot of distributions. And of course, it is important, the Poisson distribution, we all know its probability generating function, and the most well-known bivariate Poisson distribution is the one given by this probability generating function, where the marginals are Poisson, but the conditionals is a convolution of a Poisson with a binomial. And unfortunately, this model allows only for positive correlation. Having the Poisson, then we have in the univariate case, whatever the number of cluster is, the resulting probability generative function. And in the bivariate case, we might have either in the simplest form, where the cluster contains two types of individual, this one, or in the more complicated form, where I have separate clusters, this model. Of course, there are theoretical properties of this distribution, like infinite divisibility, that come from the form of these PGFs, and they are characterized, these and these are characterized in infinite divisibility. Several models can be obtained in case that xi comes from Poisson and I have a bivariate Poisson. These are the two models introduced by Holgate, the two different name and type A bivariate distributions. And my advisor, Papageorgiou, has worked on Hermite distribution, where the bivariate binomial is the number of the individuals within the clusters. And myself, I developed some models with the geometric distribution this time, which is called polyaeplik in the univariate setup. Thomas also can be obtained, the bivariate Thomas can be obtained. Thomas is actually a shifted Poissonide, is like the Neyman, but here it's shifted, and it has an impact this on the probability of the zero cell or the zero cell in the bivariate setup. Let's see the data that we discussed at the beginning, the data of Holgate. So you have here the observed numbers, and in the second and the third line are the expected numbers of each one of these combination of X1 and X2 under various models. The first line is about the Neyman type 2, and the second line is about the Thomas. So you have first to estimate the parameters from the data, and then evaluate the probabilities, and construct these metrics, and use chi-square to do the fitting and see whether the model is appropriate for our data or not. Chi-square is a very common tool when we're working with discrete data. Of course, there are difficulties here, since, as you see, there are expected numbers that are less than 5, and then you are supposed to group some of these cells. That's why you see that the degrees of freedom are reduced and they are different. And there is also a problem of choosing the best way to make this grouping. There are various ways proposed in the literature. Either you go by row and then go to the other row and to the other one, and so you have to fulfill the criteria that the expected number in itself is at least 1. We're not that strict. And then, of course, you have to subtract the number of the parameters from the degrees of freedom of the distribution of the chi-square. When we can talk about accident data, the first distribution that I would like to talk about is short distribution. Short distribution was used to analyze the accident data by the concept of spell. It's a little bit of clustering this as well, because in this concept there are time intervals that a driver is more susceptible to accidents than other intervals, and so there are accidents within these intervals, and there are also accidents outside this interval. So we can excuse here. It has to be a univariate one. It's G of U, and it is the probability generative function of the short. So if we consider Poisson number of spells and Poisson accidents within a spell, here we have Neyman, and we have also accidents outside these spells, so we also have another Poisson. From this univariate model, we can construct bivariate models, and it was my advisor that did this, adding properly either by trivariate reduction method. That's a method that is commonly used in discrete distributions when there are distributions that are additively closed. And here we have the Poisson, which is additively closed. So in this model, there is one Neyman independent with another, and a common factor, which is a Poisson. That's the third distribution. In this case, there are two independent Poisson and a common Neyman. So we can construct this model. But we can also construct a more general structure where we don't add a common factor to have a bivariate distribution through trivariate reduction, but when we are adding two dependent distributions, and they don't actually have to have the same marginals. Earlier, we have seen this model of Poisson, where both marginals are Poisson, but there are distributions that they don't have the same marginals. So here, we need one marginal to be Poisson and the other one to be a Neyman. This can be done actually in two different ways, using already established distributions like the Poisson distribution, which has been used to model car accidents, namely the number of accidents and the number of injuries. So the number of accidents is Poisson, and the number of injuries is a Neyman. So that's a more complicated model that is based on previously established models. In all these models, of course, we want to find the probabilities, but usually in discrete modeling, probabilities is not easy to be derived. And what is usually done is to derive recurrence relations. The recurrence relation might be simple, first, second order, and so on. You know, for the simple Poisson, a first order recurrence relation. But for these models, recurrence relations are more complicated, and these are the most complicated one. How do we arrive to these relations? By differentiating the probability generating function with respect to one of its arguments. So it is easy then to express, that's why it's x plus 1, because we have already differentiated, and then it can be written with previous terms. So in order to have the next term, I mean the next with respect to the values of x, I need all previous terms here, or some of them. Sometimes it's more easy, sometimes the relation is more complicated, but in general, recurrence relation is what works in these models. And of course, you need some initial value, which can be, of course, specified by putting 0 to the probability generating function, and then you get the probability at 0, 0 cell, and you need one of the conditionals by fixing either y or x to 0, and so this is usually less complicated. And of course, you need moments. Sometimes moment is not easy to derive, and then it comes cumulants or factorial cumulants. That means the logarithm of the probability generating function. And in this case, in this particular model, when I had that special summation, this structure that I used to derive the models can also help us with analyzing the cumulants using the cumulants of the initial variables I have used, these of Z1, Z2, and W1, W2, depending on whether these are dependent or not. So there's a delta here that helps us derive the cumulants. From cumulants, of course, you can have the moments and vice versa. And sometimes also it's difficult to obtain the conditional distribution. And it's thanks to Subramanian Koselakota and his work on conditionality for discrete distributions that this problem can be solved, and either by differentiating the probability generating function with respect to one of its arguments, or by using the particular structure of the distribution. Here I'm using this particular structure. It's not always the case, but in these special models, this help. And you have to know the conditional of the variables I have used to construct this model. And the one is a simple one. As I told you earlier, it was the number of injuries during some accidents, and the number of injuries are Poisson given the accident. So that's the easy conditional. The other conditional requires some combinatorial distribution here, and Stirling numbers of the second kind are involved. But in any case, you have the convolution, that means the summation of a Poisson with another distribution that might be complicated, but you can find recurrence relations for probabilities, and you know that there's a Poisson involved and something else that can be controlled. Estimation is not easy always. Either the moment estimators can be used, but sometimes are not enough because there are constraints on the parameters. So I'm presenting here model B because it uses both approaches, and you can have the marginal mean and the sample mean with respect to the variable x, and the marginal mean with respect to the variable y, and the sample mean, or the covariance. But you have many parameters, so you need something extra, and this extra sometimes had to do with the frequencies at 0, 0 cell, or the marginal frequency at 0 in either variables. So you need to solve an iteratively this system in order to obtain numerically these estimators. What about maximum likelihood? Maximum likelihood is not possible here in the way we traditionally do it, because we don't have an expression for probabilities which is analytic, and you have only the recurrence relations. For certain models, under certain families and conditions, it turns out that at least one or two of the equations for maximum likelihood coincides with this equation and this equation, that is, the two equations for the first moments. So in this case, I'm so sorry, in this case, it is safe to use moment estimators for discrete distributions, and generally they are more easy to handle. Of course, when you have nuisance parameters and so on, other EM algorithm is used by various authors and so on. These data are accident data, and these are data sustained by 79 drivers in two different time periods, non-overlapping time periods. So X are the accidents sustained in the first period, and Y are the accidents sustained in the second period. And you can see the three different models. First row are the observations, and the other three rows are the expected observation under the model's estimated parameters by the method of moments I referred earlier. Sometimes, although these models come from these distributions that we know the parametric space and it's determined, sometimes it is allowed that the parameters takes value outside of the parametric space, and we have to be really very careful during the estimation whether the estimation of the parameter is accepted as as a as a quantity or not. The fitting is rather well, but there are also other approaches. And what makes the need of the other approaches is that most of these models I referred have positive correlation. And how can change that? Because sometimes data do not have positive correlation. This can be done only through copula. And copula models have been developed a lot, but it is not sometimes easy to work with discrete distribution and work with, let's say, the tools that I have used to develop the previous models, and these tools were PGFs, probability generating functions. So let's have the Ferrier-Gammer-Morgenstern family. It's the simplest copula. What a copula do is to present the structure of correlation of the two variables using a function and the marginals. The function is the copula, the marginals we know. So this is the joint cumulative distribution function, and the cumulative distribution function of the first variable and the second variable, and here is the structure. But this is a parameter. Ferrier-Gamble has one parameter. If I work on continuous distribution, this parameter is between -1 and 1. But if I am working with discrete distribution, the whole story changes, because I have different parametric space. And this is usually the problem with copulas. When we are talking about copula function and the parameters, they are poor with respect to parameters. Usually there are fuzzy functions that have been used from the fuzzy theory to the theory of copulas. But when we're talking about the parameters, they are only for continuous marginals. When we are having discrete marginals, the parametric space changes. And so that makes models complicated. And I would like in this work to see whether I can derive the PGF of a bivariate model with Ferrier-Gamble copula. And it turned out that it was the only family from the families of copulas that I know that I could do actually it. And it was not really very simple. I had to go through the PGF of the survival function, which is possible only for discrete distributions. And the result was that in this expression is involved the maximum of two variables. So that's not an easy expression to handle. However, it was useful in deriving conditional distributions, in deriving moments, and so on. And here I just presenting you some extended, an extended model. And you can see here that I don't have anymore the survival function of x1, but I can modify it using another distribution. I have used here the survival of a geometric, and it can be easily, this result give us a bivariate Poisson distribution, different than the one I discussed you, the Gamble, as we call it, bivariate Poisson. And this can also give us good results with some data concerning the number of seeds and plants that are grown over an area. Again, you have to estimate the parameters. This requires some effort, and then the results are really satisfactory. So these are some references about the sort distribution, the polyaply, the paper that Professor Kumar mentioned at the beginning, this with the failure damper. I have not discussed a lot about weighted distributions. We can also have some weighted models to transform distributions accordingly using weights, and so explain data better. And of course, there are spatial statistics for discrete data. I did not want it to go that far, but I would like to stop here and share with you this picture and the idea that bridges are connecting different parts of LAD. And I think that congresses and conferences and events like this one connects people. And I hope that we will have the chance to work together if someone is interested in this type of distributions. So I would like to thank you very much for the opportunity. Thank you very much. Ευχαριστώ. Namaste.
Thank you so much, Professor. While I talk with Professor Weil. In fact, I think anyone has any questions, there is one or two maximum one or two questions. Oh. Now we are late, and then we can. Any of you, please.
So there are no many questions about the photos. I can show some of them again, but about the models, if somebody is interested in such type of models, can send me an email and give him more details on how we are working on this.
I hope Kalyanaraman sir, our professor is, yeah. Okay, professor. Shubha is Shubha teacher.
Yeah. Hello, sir. Hello, ma'am.
In fact,
hello.
Yeah.
Oh, hello.
So happy to see you.
Thank you for coming. Thank you for coming. How are you doing?
Yeah, fine, going on fine. So happy to see you, ma'am. It's almost 1 year now. Yeah, since we met last year.
Yeah, last October.
Yes, last October.
It's more than a year, actually.
Yeah.
Where the Dharma teacher is here in this group?
No, I don't think she's there. She's
okay.
Okay. Do you think that your viable models can be extended in this way?
Pardon, ma'am, I couldn't understand. Can you repeat, please?
Yes. If I remember well, you are working with viable bivariate distributions.
Yeah.
Don't you?
Yes. I was just thinking about that, whether these concepts can be used there. Yeah, I am working with viable.
Yeah.
So if you change the type of the inside distribution of the cluster, the XY, and this is continuous, then the whole structure gives you a continuous distribution.
Okay, okay. Yeah.
But I don't know how easy it is to handle with the moment generating functions, because you have at the time to use the moment generating function.
Yes.
And how convenient these models are for continuous data.
Yeah, we will have to work on that.
Okay.
Yeah. So how are things there, ma'am?
They are getting worse. They are getting worse these days. We are having distance classes at the universities, but not at schools. So every day we have to be very careful how it evolves. And there are partial lockdowns around Greece. If you're asking about COVID, yes.
Yes, yes. Yes.
Okay.
Professor, I would like to ask one question.
Yeah.
My question is more general question.
Yeah.
I myself, Shaktivel from Bharathiar University, Coimbatore. My question is for both Professor Arivaragan as well as to Professor Madam. I think nowadays the Indian statistics is diminishing in its look and appearance. The people using artificial neural network for modeling new data, and if things are continuing like this, the probability distributions and probability models usage will be going to be reduced, because in this information era we are getting voluminous of data. So modeling a voluminous of data, I do not know how the probability model withstand the fast computing of artificial neural network. Anyone can elaborate how the probability model will survive with this new computing facilities, whether it has changed its dimension? It's not only to bivariate and for univariate and multivariate cases also.
Well, if I can answer, there are also, besides the estimation procedure, there are also theoretical properties that we are interested in. I refer to infinite divisibility, which is a very central idea behind distributions, and characterization results that determine which distribution to use. So this cannot be passed by the computer evolution, and of course let's say the tools that we have to make estimation and kernels estimations and so on, that can fit data well. You have behind to have a model and be able to predict using the model, instead of let's say having a computer system that you expertise it in doing so.
Yes,
I don't know if I've answered.
I got the answer. The properties is very important in terms of application. Perhaps the artificial neural network may have advantage, but as you said, the properties play a vital role, giving a base to those applications. Thank you, madam. Thank you.
Thank you for your question.
Thank you.
Okay, if there is no questions, let us conclude the session. I think you can ask the questions, etc., through email or other ways also, no problem. It is better to find some other media. Like anyway, we are very lucky to have these professors today, to have a very excellent manner, they have presented the ideas, even though they are complicated and very advanced things also in a very nice way. And I, on behalf of the Department of Statistics and School of Physical and Mathematical Sciences of University of Kerala, I extend and all some both in the Google Meet and the other streaming live streaming. I utilize this occasion to extend our heartfelt gratitude to both professors, Professor Arivarignan and Professor Violeta, for your nice talks and your support to our department. And in fact, we expect your continued support and blessings to our department in future also. Please take care of. And in fact, there are several participants. In fact, we have limited the participants in the Google Meet platform, but because to avoid disturbances, network disturbances, etc. Even then, only the senior professors and some selected professors were only allowed, and our students, some of the students were really interested students were allowed in the Google Meet, and others are watching through Facebook media and other media. They will get all those things. And on behalf of the department, in fact, I am very much lucky to have a very nice personalities and experts in the statistics, like our Kalyanaman sir and Dr. Shaktivel also there, and several are there. I'm not extending too much everyone's name. There are a lot of Professor Subrata Chakravarti also was there, and several are there, in fact, from several parts of the world, in fact. I utilize this occasion to thank each one of you, professors and researchers and our students. And my colleagues also were there in the support. Hi, Sattar, Abdul Sattar, Manoj. So they were there. They are also. We can find some time to interact in future. That's better. I extend our gratitude, our thanks to my colleagues and those who supported me in materializing all this in a better way. And our research scholars, our MPhil students, MSc students, and the other participants, all I extend our thanks to each one of them. Okay. Above all, Dr. Baiju is there. Several teachers from our colleges and other universities also there. So thank you all. Thank you, each one of you. Now there is time. We can either we can conclude and leave, or otherwise, if you want to say anything, you are all welcome. Some more time we can spend for that. Anything you can communicate. I think so. No problem. 5 minutes we can spend in that way. If we okay, process. Baiju, Dr. Baiju, Kalyanan sir is trying to speak.
Friends, it's a great occasion to be back in the department for a long time. And very nice to hear about cumulants after a long time, because I started forgetting all these things. So, nice presentations too. And Satish, Manoj, Sattar and their team are doing wonderfully well. I am really feeling very high to see people working in the department like this. I am very happy to be part of the entire program. After 20 years, I am seeing this means it's really God's grace that I'm able to be part of the programs in the Department of Statistics, where I spent a major part of my life until 2001. Thank you, Sadish and team, for the excellent program that you are organizing very regularly, and hope that you continue this for many more years to come. And this is one of the major facilities that is available so that we can meet very often with programs of this type and able to see a lot of information that is flowing out. In fact, I had been teaching structural equation modeling for about 28 years. Sharing it after 20 years is something that is making me a little energetic again. So I thank both speakers for presenting a wonderful presentation over the last 2 hours. And once again, I thank Satish, Manoj, Satar, and all others in the department for providing this opportunity. Thank you all. Thanks.
Thank you, sir. Thank you so much. Thank you. Doctor, something he has to earlier has to speak. Dr. Baiju.
Okay, sir. It is a very nice program, and the presentations are very good. And the two resource person, Advirgna sir and Madam, also presented in very well. And this is a very nice function. I congratulate Sadish sir and the team for arranging such a wonderful session in the World Statistics Day today. Thank you, sir. Thank you.
Thank you. Thank you. Thank you, Baiju. Thank you all. Now let us meet again. We can find some occasions to arrange like similar gatherings via our online platform. We are always grateful to each one of you, professors. Your encouragement and blessings are the reasons for arranging everything in this way. And once again, thanking you and thanking Professor Arvind sir and Professor Violeta. Please kindly accept our extent of heartfelt gratitude. Once again, thanking you all. Let us conclude the program. Thank you all. Thank you so much.
Hello, sir. Thank you, sir.
Yeah. Yes, someone. Okay. Yeah, madam.
Thank you for the invitation. Thank you for the invitation.
Oh, happy.
It was a very.
Yeah. Okay. Okay, madam. Yeah. Thank you.
Thank you, sir. Thank you, sir.
Happy World Stats Day to all. Yeah.
Happy World Stats Day, sir.
Chinani, yeah. 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 Hello, Rosmi. Ditto.